that you guys are going to do a lab on it on Thursday. So what we do here, especially the last example, it's like, oh, I've seen that before, and you have. All right. So what the Clausius clapeyron, I can never spell it. So right off the bat, Clausius clapeyron is CC. That's just a CC. We have a CC equation and a CC plot, Clausius clapeyron. All it looks at is this idea. If I were to tell you if I were to tell you that the heat of vaporization keeps increasing, remember the heat of vaporization is something going from a liquid to a gas, so it's getting harder and harder. What would you tell me with regard to the intermolecular bonds? And getting stronger and stronger, because if heat of vaporization is increasing, that means it's harder to break the bonds. So if heat of vaporization increases, I'll do it this way. Oh, goodness. Increase in heat of vaporization, delta H vac. Yep. So you figure that's got to be increasing IMF, intermolecular forces or intermolecular bonds. Cool. So what does that do for equilibrium vapor pressure? Will your equilibrium vapor pressure of a substance be higher or lower if you have a high heat of vaporization? Yes. Low equilibrium vapor pressure. I'll put EVP for equilibrium vapor pressure. That's a mouthful. So the Clausius clapeyron plot, equation and plot, make use of this idea that with increasing heat of vaporization, that means we have lower equilibrium vapor pressures. Put another way, with decreasing heat of vaporization, what trend do we see in equilibrium vapor pressures? Increasing. Yep. That's what the Clausius clapeyron plot looks at, or the equation and the plot. And it assumes that the heat of vaporization, it's funny because we just assume that you can look up a heat of vaporization for a substance in a table or online or whatever. And we assume that it's good over a range of temperatures. So if your delta H vac is pretty constant, heat of vaporization for a liquid at 100 degrees versus that same liquid at 200 degrees, if that's pretty constant, then we can actually kind of make this a relationship between the temperature and the equilibrium vapor pressure. Okay. Didn't totally rush that, but I did just a little bit. So this actually is a Clausius clapeyron equation. So picking it apart, there on the left, we have, what's ln?
Natural log.
Natural log, exactly. We have the natural log of the equilibrium vapor pressure. Natural log of the vapor pressure is equal to negative heat of vaporization, that's got to be a constant, divided by R as a constant. And what we're going to do is we're going to take that same liquid and we're going to submit it at different temperatures. So, let's look at what that trend would be. If you have one substance, not different substances, but just one substance, what happens if you increase the temperature? What happens to the equilibrium vapor pressure? You increase the temperature and it will go up. Yep. So that's actually kind of what we're doing here. Delta H vac is heat of vaporization. R is the ideal gas law constant, but we're not going to use the, we're going to use the one we used in thermodynamic problem. T is the temperature, but it has to be in units of Kelvin. And C, I'm going to show you how this works, but in math, if you plot a straight line, you get kind of some kind of little thing on the end, C, and that's the constant of integration. Like y is equal to mx plus b, that's the b part. Speaking of y is equal to mx plus b, notice the difference between the previous version and this version is I have pulled out the inverse, or the 1 over the absolute temperature. I did that on purpose. Why? Because this thing right here is a constant. So, especially in Chem 2 and physical science in general, we plot things. So, if we plot along the y-axis the natural log of the equilibrium vapor pressure, and if we plot along the x-axis the inverse of temperature, so I'm going to kind of show you what a Clausius-Clapeyron plot looks like. So along the y, we have ln of p, natural log of p. Now remember, that's equilibrium vapor pressure. And along x, we have the inverse of temperature. Then we're going to end up actually with a negative slope. And that slope is going to be equal to negative delta H vat over R. That's how that works. Right. And so y is equal to mx plus b. Isn't b like the y-intercept then? So these are, let's see, 1, 2, 3, 4, 5. 5 different substances, and these are Clausius-Clapeyron plots. And you can see for each, it's like 1, 2, 3, 4, 5. Looks for each in general, they went ahead and, this is what you can do in the lab, they went ahead and changed the temperature, like what the temperature was, converted it to Kelvin, took the reciprocal of it, and that's what's along the x-axis. And they took whatever the equilibrium vapor pressure was, they took the natural log of it, and that's what's along the y-axis. Okay, so for each group. I went ahead and printed this out because I use it for the next problem. So, Merry Christmas. So these are different substances. Now, to me, when I look at the Clausius-Clapeyron plot, I can't really make some of the judgments I make about some of the other plots I look at. I can't eyeball that and think, oh, well, that means there's stronger intermolecular bonds or something like that. Okay. These are Clausius-Clapeyron plots. Nice linear relationship between the natural log of the equilibrium vapor pressure and the inverse of the absolute temperature. I'm not real thrilled about how this particular x-axis units are, because whatever number you pick off, you have to take it times 10 to the third. Or it is times 10 to the third. I don't know, I just think it's confusing. Okay, so here's a question. So if we find aniline, or benzene, we find benzene on our curve, question here is, what temperature in Kelvin is needed for benzene to have an equilibrium vapor pressure of 116 millimeters of mercury? I have no idea. Well, if we're going to use this data, notice that we have 116 millimeters of mercury, but over here, this is the natural log of equilibrium vapor pressure. So right off the bat, all I'm going to do is take the natural log of that. So if you have your, calculators handy, find your LNP, which I don't use much, and take the natural log of 116. Okay. So that's how it's going to show up along the y-axis. This. So now that works. So if we find on our paper 4.75 and we see where it intersects with benzene, oh, it's kind of on the 3.3 mark, right? Okay. So we're getting closer. But remember that 3.3 is actually 0.0033 just because of how it's written. Sorry. Okay, so at the 4.75, we end up with 3.3 times 10 to the third. But it really means, again, I just think of it this way. We picked up 4.75. This guy down here on a normal plot, that would have really said 0.0, say 1,000, 0.33. Sorry about that. That's what the times 10 to the third means. Okay. All right, so now we need to basically unpack that temperature. So to unpack it, we are going to take the inverse of it. Does that make sense? If 1 over t is equal to this, then to get t, I'm going to take 1 over that. Exactly what we're going to do. If you take the inverse over 1 over 3.3 times 10 to the third, okay, you're actually going to get t, and units will be Kelvin. So go ahead on your calculators, and I have a 10 to the negative 1 t, so that's kind of, or just take 1 divided by 0.0033. Okay, you get that. 303 Kelvin. That is the temperature on the Kelvin scale from this Clausius-Clapeyron plot, at which the equilibrium vapor pressure will be 106. That's hard to say. Equilibrium vapor pressure will be 116 millimeters of mercury for the compound benzene. Okay, so a couple little tricks there. That's how it looks. What else do we need to know about the Clausius-Clapeyron plot? Well, that's the Clausius-Clapeyron equation. So I think I've already said that along the y-axis we plot the natural log of equilibrium pressure versus the reciprocal of the absolute temperature along the x-axis. We're going to get a straight line, and the m portion that I kind of teased out from the Clausius-Clapeyron equation, the m is going to be equal to negative heat of vaporization over R. I think on a few slides ago I told you which R to use, right? They did. Well, the value for R we're going to use is one that goes back to the thermodynamic value for R, which they're all the same, but the units work out well. 0.00831 kilojoules of energy per mole per Kelvin. All right, so here we go. I'm going to talk you through, remember I said, you started the lecture, I'm like, well, that's what you're going to do in lab. So here's where it is. That's what you're going to do in lab. Okay? So for instance, you're not going to use nitric acid, you guys are going to use methanol. But what we can do is run a substance, in this case, increasing temperatures. So what should happen to the equilibrium vapor pressures? Should go up. Net increasing temperature, increasing equilibrium vapor pressures. So here they are in millimeters of mercury. Okay, so actually, I think you're going to see this plotted. Now, when I plot this, is this a Clausius-Clapeyron plot? No. Okay. So I'm going to take that raw data, and I am going to prepare a plot just of equilibrium vapor pressure, not natural log, and not the reciprocal of the temperature, just the temperature, and you're going to see kind of this nice exponential curve. And then we're going to go ahead and do the real thing. The Clausius-Clapeyron plot means that we're going to have to take the natural log of those pressures, and we're going to have to take those Celsius temperatures. Anyway, we're going to have to make sure they're in Kelvin and take the reciprocal, and that's what our plot's going to be for a Clausius-Clapeyron plot. And then what we're going to do with this nitric acid data is to go ahead and, you know how Logger Pro gives us a slope. We're going to use that slope then in this relationship to knock out the heat of vaporization. That's it. So this is that first plot I was telling you about. This isn't a Clausius-Clapeyron plot because it's simply not the natural log of, but it's the equilibrium vapor pressure along the y-axis. And we have temperature, it is in degrees Celsius. So we're going to have to get those to Kelvin and take the reciprocal. So a nice, actually should be a logarithmic relationship that we tease out of it by using the Clausius-Clapeyron equation. So here's our raw data again, and in Logger Pro, it's great at making calculated columns. And so we're going to do that to get to absolute temperature. We're going to add 273. To get to the inverse, we're going to take calculated column. We're going to take basically 1 divided by this column. And then we need to go ahead to, this is a calculated column based upon our equilibrium vapor pressure. So we just take the natural log of the second column. So finally here, these last 2 columns, these are ready to plot. I'm going to talk you through, this is what Logger Pro will look like. In your calculated column, you'll put an equation here, and it will be the temperature column plus 273.15 to get in Kelvin from Celsius. Now, I haven't emphasized this much, but when you do your calculated columns, you have the ability to click on the option button at that point. The options look like this, and this can be helpful where you go ahead and, for instance, I'm going to go with 1 decimal for my temperatures. You can tell it either decimals or sig figs, and decimals make sense for this one. This is the calculated column to go ahead and get our reciprocal, our inverse of temperature. So we're going to take 1 over the absolute temperature. And here, I'm going with 4 sig figs, my options for the calculated column. And here we're taking the natural log of the equilibrium vapor pressure. So in Logger Pro, you're going to do ln, begin parentheses, and then pull in that vapor pressure column, end parentheses. And then what works well probably in this case was to go with 3 decimals with our natural log. And ta-da! There's our Clausius-Clapeyron plot. Correlation coefficient is great, negative 1.00. So here in a minute, we're going to calculate the value for the heat of vaporization. We're going to go with, use that negative 4.64 times 10 to the third. That's what that means, to knock out the heat of vaporization from the slope. So I'm careful. I always write it down and then rearrange it. So if we have this relationship between the slope and the heat of vaporization in R, the heat of vaporization is equal to what? Negative MR. Okay. So we're ready to plug in. There we go. So the slope we came up with was a negative, I don't like how my slides are. I really think it should say delta VAP is equal to negative MR, and there's a negative there, and I think there should be a negative there. I think there should be 2 negatives. Units of the slope are Kelvin, and why that would be is slope, and actually we're going to do a problem like this here in a minute. M is equal to change in Y over change in X, and units for the natural log are unitless, okay? But units for the change in X are 1 over Kelvin. So that gives units anyway for the slope is Kelvin. Units of the R are kilojoules per mole Kelvin. So of course Kelvins cancel, that gives us heat of vaporization in terms of energy per mole, which is perfect. Rounding to 3 sig figs, I get 38.6 kilojoules per mole. So since I've been telling on, like, I don't know, it's TMI, too much information, but I had a date with my husband yesterday afternoon. We went to the lab and we did the experiment that you guys are going to do on Thursday just to make sure it worked okay and what pitfalls to watch out for. So anyway, we did it for methanol, and we came up with 2% error. 2% error, people. See if we can do it. The gauntlet is thrown. For your lab on Thursday. But anyway, so that's the heat of vaporization for nitric acid. What's that?
I prefer 1200% error.
1200.
That one time.
Well, you know, pays the bills. Okay. So a follow-up question. We can use that graph. We're going to go back to that graph. I didn't print out, but you guys have it. To answer this, now that you have the Clausius-Clapeyron plot for nitric acid, what is the normal boiling point temperature? Remember, normal boiling point means normal boiling point temperature for nitric acid. So it's been a while. It feels like this unit has already been 2 units wise. But the definition of the normal boiling point temperature is when the temperature at which the equilibrium vapor pressure is equal to 760 millimeters of mercury. Of course, the importance of 760 millimeters mercury is like normal atmospheric pressure. So it's the temperature at which your equilibrium pressure is equal to normal atmospheric pressure. Okay, so we're going to use our plot to tease out this information. Okay. So in order to use our plot, it's kind of like we did before. Our Clausius-Clapeyron plot has the equilibrium vapor pressures. The natural log of the equilibrium vapor pressures. It doesn't have the equilibrium vapor pressures. So to tease it out, we're going to have to take the natural log of that 760. So along our y-axis, we're going to find the value 6.633. Actually, now I remember I have it in my slides, so we'll have to go back to it. So along the y-axis, we're going to pick out 6.633. And if you've got to kind of go looking at it, we're going to actually have to use what's called extrapolate instead of interpolate. Now there's you're like extrapolate, interpolate. Think extrapolate extra. So all it says, all of our extrapolation, the reason we have to extrapolate is there's our last data point, and what we want is up here. So that's extrapolation. We're going extra, beyond the last data point. Interpolation is what you guys have done, what we do other times. Like if it's right here, that's interpolation. This is extrapolation. Small. Okay, so we can use LogRPro to do that. So remember, LogRPro has that, I think it's called, I don't know, maybe it's interpolate or extrapolate. But up here you can see where we've gone beyond the last point, and here is that 6.63. So that is the natural log of 760, about. So the reciprocal temperature we're looking at is 0.00281. So we're going to have to do what we did before. We're going to take 1 divided by that number to get the temperature in Kelvin. So the inverse of the temperature is that 0.00281. Units are inverse kelvins. So to get the temperature, and I don't have it here, so I'm just going to go ahead and try it out. To get the real temperature, if you take 1 divided by 0.00281, okay, you get that 356 Kelvin. Whoosh. So probably, and I can't remember, I gotta finish out my slides. Kelvin's not a temperature that most people deal with. It's, well, Celsius probably more likely. So to get to that, to Celsius, what do I have to do? Subtract 273, exactly. So if I take 456 minus 273, I guess it's 83 degrees Celsius. So according to our Clausius-Clapeyron plot, the normal boiling point temperature for nitric acid is 83 degrees Celsius. All right. Another problem. Come up with the heat of vaporization for diethyl ether. Okay, that can't be too hard. But there's a catch to this. We're not going to use log or pro. We're just going to be given these two ordered pairs. So they ran it twice. They, at the temperature of negative 22.8 degrees Celsius, the equilibrium vapor pressure of this volatile substance was 57.0 millimeters of mercury. They ran it at a second temperature, about room temperature, 25 degrees Celsius. Not so surprising, the equilibrium vapor pressure went up to 534 millimeters of mercury. So we only have these two data points, and we don't have access to log or pro. So my suggestion usually is to think of it as putting those on a plot. So everything you would need to put those on a plot. So for instance, it looks like this. We would need to take those two equilibrium vapor pressures, and we would need to take the natural log of them, because that's going to go along the y-axis. And we would also need to convert those Celsius temperatures into Kelvin, and then take 1 over that, and that's going to go on the x-axis. And then kind of picture that, and I kind of erase this. But if we call, the first one 0.1 and the second one 0.2, I mean, this is what you have. So that's what you have. And so we need the slope of that. Okay, and like I said before, the slope is, I think it's on this next slide. Well, so let's go ahead and get things ready. So we can't do the Celsius temperature. We got to get it to Kelvin. So we're going to add 273.15. I think we had talked about this. That notice I'm not going to stop with just 273 because actually the temperature I need to adjust has at least 1 decimal. So anyway, the first temperature was at 250.4 Kelvin. That corresponded to a pressure of 57.1 millimeters of mercury. Need to fix the second temperature. We take 25.0 plus 273.15. We get 298.2 Kelvin. And the second pressure, then remember, was a higher equilibrium vapor pressure of 534 millimeters of mercury. So there's our numbers ready to do something with in our ordered pairs. So what I started to say over here is we know that M, the slope, is equal to negative heat of vaporization over R. We also know that the slope is change in Y over change in X. It just is. And change in Y is, you can go y1 minus y2, or I usually go y2 minus y1. Change in x is x2 minus x1. So, do you see where I'm going with this? Here in a minute, we think of this as, well, anyway, I'm not quite going there yet. Okay. So Y2 is the natural log of the second pressure, P2. Y1 is the natural log of the first pressure, P1. In the bottom, we have 1 over T2 minus 1 over T1. Now, I might give you equations here and there, and I was pausing because I can't remember. Did I tell you I gave you an equation sheet for this first unit exam? No, I can't remember if I did or not. I know I did the second one. Oh, that's right. I'll have to double check. But I wouldn't give you this equation because you should be able to get this from what you know about the classical coupled plot. Now I'm going to show you something nice, something fun with regard to logs, natural logs or log base 10. If you have a difference of two values, that actually does something cool because it can be we can rewrite it as the natural log of P2 over P1. So I took this one, the natural log of P2 minus natural log of P1 is equal to natural log of the ratio of P2 to P1. How fun is that? So I think this is actually my last form that I'm ready to plug in. I'm ready to go back to the box that was on the top of the previous slide to pick up my P2 and my P1. Notice that we have some cool things happening here. Of course, these units are going to cancel each other, right? The units of P2 and the units of P1 are the same, so they'll cancel each other out. And we have, of course, the inverse of the absolute temperature. That would give us our slopes of Kelvin, because of the denominator. So here's what it looks like. So plugging in numbers from the previous slide, we have the natural log of the ratio of 534 divided by 57.0. Notice I didn't bring along the millimeters of mercury, but I could have, but they're going to cancel out anyway, so I just didn't. So that's the ratio of P2 to P1. In the denominator, we have 1 over T2, which is 298.2 Kelvin, minus 1 over T1, which is 250.4 Kelvin. Now, if you haven't done many of these, I don't think I'm going to take the time to plug it into my calculator, but if you haven't done much with natural logs or inverses, you might want to crank it out a few times. See if you can get it right. Crank it out. So for me, I take the natural log, begin parentheses, which already gives me parentheses, 534 divided by 57, close parentheses, divided by, how's inverses tracking this? I'm going to begin parentheses. I think I'm going to use my x to the minus 1 here. Try that. So 298.2 x to the minus 1 minus, that looks like it's going to work, 250.4 x to the minus 1, close parentheses. I got negative 4 sig figs, 40,490. I got actually negative 5. So, anyway. So, any questions about that? That's our slope. And we did it without log or pro, and we did it with just 2 points because you only need 2 points to make a straight line. So you're going to want to be able to do this too. So you know what's next is that's equal to M, okay, and we're after heat of vaporization. So the heat of vaporization is equal to negative MR. So we're going to bring our slope, see here I did it right. Heat of vaporization is equal to negative 3,494 Kelvin times R, which is 0.00831 kilojoules per mole Kelvin. The Kelvins cancel out, we have units of energy, kilojoules per mole, which is awesome. Rounded to 3 significant figures, we have the heat of vaporization, dun dun dun. It's 29.0 kilojoules per mole. So again, this is just a way of using the Clausius-Clapeyron equation, Clausius-Clapeyron plot, and 2 points, pressure and temperature, to come up with the heat of vaporization. Is that the last slide? Dun, dun, dun. I am sorry about the other day where I didn't have the part out there for the answer key. That's part of why I'm delayed. I have to find the answer key or make one. I don't know. Just give everybody 10 for handing in, was it part 6 I didn't have out there? So I didn't do it on purpose. Or did I? So I think that's quite enough for today.